My name is Adam Rosenblum. I'm giving a presentation in ECH4934, which is also a professional seminar for chemical engineers. My presentation is on green chemistry within biomass transformation to energy. So I wanted to focus on green chemistry because I like to read into the environment, and green chemistry is the design of chemical products and processes that reduce or eliminate the generation of hazardous substances. And the main goals are to reduce environmental, health, and safety risks by redesigning toxic molecules, synthetic routes, and industrial processes. And it's a very broad area, obviously. There's chemistry, chemical engineering, all types of engineering. And we wanted to focus on chemical engineering, and one of the main issues is transforming large amounts of biomass efficiently to energy, and most of the processes now make it very unsustainable. So there's 12 principles of green chemistry, just a few of them. Waste prevention, obviously you don't want a lot of waste, you want the least amount possible. Designing safer chemicals, so a lot of chemicals are really toxic and not the best to use. Catalysts speed up reactions, so they're more energy efficient. And real-time pollution prevention, but you don't want pollution, so it's preventing it essentially. Oh, there we go. So what is biomass? So biomass is plant or animal material used for energy production. It can be grown crops, wood residues, food waste from crops, animal farming, or human waste from sewage plants. And wood is very commonly used because trees are very accessible, which further adds to the problem because like deforestation. So the reason the process isn't sustainable now is wood is one of the top choices, and if too much is taken, it takes decades for trees to grow again and capture the carbon emitted initially. So there's carbon debt, and plants start with carbon debt because when you cut down a tree, it's already captured like so much carbon. By the time it regrows to where it was, then that's when it's carbon neutral, and then past that point. And trees take decades to grow. So the cycle of biomass energy, there's a lot of things it's used for here. You see it goes from the trees, the lumber industry, then the wood residues are used as biomass, the transporting, the factory, the shipping, and all the other transportations, not just shipping in trucks across like continents, and then power plants. And then those emit CO2, and the trees are the ones taking up CO2. So when you cut too many trees down, there's a huge amount of carbon lost, and it's unsustainable. So the goals are making the biomass process sustainable and making sure the process used follows the principles of green chemistry. So to make the process sustainable, you need innovative processing technologies, so just new processing technologies that are more efficient than the ones used right now. Separation and depolymerization processes, which is separating and making big polymers, breaking them down into monomers. And monomers are like what make up a polymer. And catalytic conversion systems. And catalytic conversion systems are basically they take bad toxic pollutants and convert it into less toxic pollutants. So it makes it cleaner and safer for the environment. And the premier alternative used today for it are ionic liquids, and these liquids have emerged as a leader in more sustainable biorefinery due to their ability to reduce the release of volatile organic compounds. They have an extremely low vapor pressure, which is a very big breakthrough because most organic solvents used today have very high vapor pressures, and that's the main thing that makes them unsustainable. So a few examples of ionic liquids. They do carbon capture and liquid membranes. That's how they separate. And remember, you need separation and polymerization processes. They're working fluids for heat storage, lubricants like oil, and surfactants, which are just like reactants on the surface. And then they're green solvents, which goes with our principles of green chemistry. biocatalysts, chemical processing, protein crystallization, and chemical processing is for the biomass processing, so that's a big one. And then advanced materials, pharmaceuticals, which is a very big industry they're used for, and fuel cells and electrolytes. Fuel cells are put in cars, they're hydrogens. So this is kind of the method of how it's used. You take the biomass in the ionic liquids and it makes cellulose, hemicellulose, and lignin, and then those go into an integration of sustainable energy conversion and separation strategies. So just a whole bunch, and there's chemical pathway for more the chemistry side, and a biotechnological pathway, so the technological side, and they're more sustainable fuels, chemicals, and materials all produced from this biomass. So the result, all the components of biomass are soluble in ionic liquids. By using ionic liquids, we can make biofuels, fine chemicals, electricity, and renewable energy. And ionic liquids follow the principles of green chemistry and make the biomass process sustainable. And that was our goal from the get-go. We wanted to follow the principles of green chemistry and make the biomass process more sustainable. So in conclusion, if done using ionic liquids, the biomass transformation to energy can be more sustainable and follows the rules of green chemistry. And then renewable energy is obviously still emerging in a modern day society, and tons of research is being done on how to make more sustainable processes, whether it be biomass, solar, wind, or hydropower. So there's still tons of breakthrough and research going on with these types of energies today, and as the days move on, there'll be more and more breakthroughs. And then I'd like to give some acknowledgments to these two articles which I used. This first one was about biomass in the process, and then the second one was more about the role of green chemistry in biomass processing. So they were really helpful. It's how I found out about ionic liquids, and I'd like to thank my audience for listening today.